Welcome. My name is Opubo Benebo. The interlude during subsistence farming, obtaining between the end of planting and the start of harvesting, is in fact a grace period to mentally reflect on the post-harvest context and the advantages and hardships that may be arising from the context. After all, the farming operation is not expected to be a one-off operation, but rather an ongoing operation, and hence requires continuous improvement, and the looming post-harvest context is the sort of rinse-repeat circumstance that needs to be fully embraced to evaluate those operations of the key functions that require improvements of the underlying technology, improvement, retrofit, designs. Given the object of using the biotic waste as energy resource for subsistence farming to produce biofuel, activities of producing biogas certainly achieves the goal. So one of the rational things to do then is the recycling of the biotic waste through energy resource, energy contents extraction process that is compact enough and demanding of elementary skills as to be readily adopted for and in subsistence farming, and permits subsequent processing of the output for energy extraction for use in the operations of the farm. Admittedly, at this time, there are several energy extraction or resource pre-processing technologies proven and viable and therefore competitive in being adopted for subsistence farming. Yet, in actually selecting one from the many, there is the overriding constraint of simplicity of design and minimality of cost. The technology options hemicellulose microbial fermentative utilization that causes the utilization of the biotics into sugar. Biotics pyrolysis that pyrolyzes the waste into syngas and syn oil. And anaerobic digesters that digest the waste into biogas and digest it are such that the one technology that meets the condition of simplicity and minimality of cost of adoption is the anaerobic digesters. Besides, anaerobic digesters prefer the best option for the low skill set requirements and for recycling of the biotic waste to produce biofuels. The biotics used as feed for anaerobic digesters can produce biogas. Even so, operating of a bioreactor, of which anaerobic digesters is the class, of course, admittedly requires certain specifications. These specifications at a minimum include energy demand load, additional nutrients need for the microorganisms engaging in the metabolic digestion of the biotics in the digester, energy storage needs, or continuous no storage needs. So the advancing of any bioreactor design must necessarily first collect together a set of specifications capturing the characteristics of the operational bioreactor. In synopsis then, this episode entitled Subsistence Farm Biotics Gas-Biofuels provides a design for deployment in subsistence farms for the conversion of the chemical energy in the hemicellulosic waste into a gaseous state on which the design of the electric power generation is partially based for operations. Retrofit engineering of a process that allows an integration with operational deployed sub-processes for a coherent operation. Components selected to ensure stability and controllability of the integrated process, and also integrates well into the farm process automation control system. The driver rationale guiding the effecting of the processing of the gas biofuel has the object of processing the waste to provision biogas and as byproduct the digestate that comes along. Yet, first off, the design specifications for the energy requirement for the operations of the farm. The energy demand of the farm, as can be noted, includes, for instance, the electrical powering of the pumps used in the delivery of the water from the water reservoirs to the farms and subsequent dispensing of the water onto the produce. There are also other potential uses of the energy for traditional farming that would have to be addressed. For instance, even harvesting often entails energy use. Even the mere use of wheat cutters would require energy use. So, to have a better sense of the energy demands, the totaling of the energy demands of these tools and activities need be summed up to define the energy load of the farm. In order that the evaluation be as realistic as possible, the energy usage for each tool and activity would have to take into account, together with the frequency of the use as well, and then sums average over per unit time, such that the kilowatt hour of the production system is accurately determined. This is critical so that a prevailing good appreciation of the design shortfall or over-design is reliably assessed for the efficient management of the operations of the farm. Ordinarily, the operating of a bioreactor requires the co-feeding of nutrients into the bioreactor. However, this is not really the case with anaerobic digesters. With this class of bioreactors, the biotic waste is also considered of all the nutrients need of the microorganisms, both macronutrients and micronutrients. The former often provisions the microorganisms with energy, while the latter provisions the substances for growth. Although the nutrients are usually microorganism specific, the biotic waste, being of generic nutrients, can be customized with the addition of specific nutrients to form a composite nutrient mix better suited for the specific organism of choice. Customizing the intrinsic nutrients can be made readily with selections from options of collected nutrients scoped by improvisation from everyday resources as to be reasonably generic for all microorganisms. The nutrients pool offering the options can be scoped from as Epsom salt, seawater or sea salt, tomatoes, citrus, fruit peels, pineapple, ginger, and by preference only vitamins. Seawater is for the minerals, as is Epsom salt is for magnesium. Pineapple skins are generally offer zinc, tomatoes for nitrates and nitrites, and everything else that needs to be added. As design guide, the standard dynamics of anaerobic digesters in operations are adopted. Admittedly, most often anaerobic digesters are designed as a batch bioreactor, and so that option of use of batch bioreactor is always available as a default fundamental. But the design of one large reactor may not be well suited to the needs of the small space being delegated to the subsistence farming project. However, the specifics of the design rest on the management of the reactions set that constitute anaerobic digesters, which are hydrolysis, acidogenesis, acetogenesis, and methanogenesis. And an analysis of the reaction progression dynamics would be worthwhile and may suggest further guide. These four reactions have stage-specific reaction times, which sums up to give the reaction time of anaerobic digesters. So then, the design for the farm would require an optimization of the choice available. Assuming these times to be fixed, then dividing the waste, say, into a number of portions for a smaller reactor volume means the biogas will become fully available at the set number times the reaction time. Of course, this offers the chance of the waste actually rotting away somewhere along the way. The rotting of the waste, of course, could be prevented with the forcing of an overlap of the digestion process, resulting in the shortening of each batch reaction time. Assuming there are 4 same-size reactors as for the many portions, then the batch started in reactor 1 gets pushed into reactor 2 after, say, the first stage reaction time lapses and a new batch is started, and then repeat again after the first stage reaction time passes, together with the batch in reactor 2 pushed now into reactor 3, such that all is pushed sequentially forward. Then the net result is that the total waste will get treated in less time than the default many portions multiplied times the batch reaction time per anaerobic digester. Bounded then by the time to rotten and anaerobic reaction time on space availability, then the optimum performance time span would be determined with the number of portions. Then, of course, the number of portions, therefore, is then determined from the difference between the rotten time minus the reaction time and the result divided by the product of the interval of shift and the reaction time. Now that the number of portions can be determined, then the total waste volume is divided as analyzed to determine the size of each volume of portion. The batch reactors are then designed to hold that volume, and 4 such reactors are manufactured and stacked up either vertically or in pairs, but linked to form a series bioreactors, and each connection is fitted with a check valve that lets material flow only in one direction. The bioreactors are all sealed, but the contents are progressively pushed into the next one at the set time. And then the farm will technically have that quantity of gas per day to use for over the same number of days as the portions count. So while a single stage reactor gives the output all at once, the smaller reactor set will produce it in longer time frame, but also better manageable. Yet the bioreactor system structure and construct impose certain additional specifications that must necessarily be adhered to for the system to perform as expected. One such critical requirement, though, is that the reaction time of the batch anaerobic digesters must be equal to the sum of the 4 shifts reaction times, commonly known as the residence time of the individual semi-continuous flow bioreactor of the bioreactor system. Another criterion which addresses feed conversion comparison is the production ratio. For instance, the quantity of production divided by the total batch reaction time must equal the unit time production volume of the bioreactor system. Of course, this criterion is a superior requirement for operating the bioreactor system, such that the sum of the residence time equals the batch reaction time. The design of the first reactor, except for limited differences, will be much like the middle 2 reactors. The fourth reactor, however, is significantly different from all others because of the accommodation for the 2 effluent types. The presentation of the designs group the first 3 reactors with one design and elicits the differences of the first by simply highlighting it. However, the fourth reactor will have to be presented separately because of the extensive differences. The sequential batch anaerobic reactor digester reactors have a design of a single cylinder, each capped at the bottom and top, and towards the top of each on the side is a feed port, and at the center of the bottom cap is an outlet port. At the center of each top cap is a stirrer spindle with impeller section in the cylinder section. The end of the spindle is affixed with a motor for turning the spindle. However, the first reactor also has off-center on the top cap a smaller tube that has check valve midway that lets liquid flow in but is airtight to the outlet of any matter. The top of the tube is connected to the nutrients customization feed tank if one is adopted, but operated in batch mode. Also off-center on the same cap, there is another tube also fitted with a check valve that allows gases to flow out but not in, essentially the inverse of the nutrients tank. The equipment design of the fourth bioreactor module is far more complex because this bioreactor is a three-phase system: liquid, gas, and solids, and not only the inlet of particulate liquid suspension, but the inside the bioreactor formation, best described as nucleation of granular solids within the suspension that must be extracted, and the nucleation and growth into gas bubbles also within suspension that must be pulled out. As with the other sequential batch anaerobic reactors, the fourth reactor has similar design base. A design of a single cylinder capped at the bottom and top, and towards the top on the side is a feed port, and at the center of the bottom cap is an outlet port. At the center of each top cap is a cylinder spindle with impeller section in the cylinder section, and the end of the spindle is affixed with a motor for turning the spindle, so the suspension is being steered as the Biotics suspension. However, the reactor has off-center on the top cap a gas flow through check valve pipe device for the gas outlet. Also off-center on the same cap, there's another tube also fitted with a check valve that allows gases to flow out but not in. At the center of the bottom cap is an extraction device for the solids outlet. The solids are discharged in a transport bed flow. In a rural setting, a blacksmith will help with the fabrication and assembly. In a more technological setting, a mechanic in a machine shop might be engaged for this same help. The adoption deployment of the fourth set sequential batch anaerobic digesters bioreactor system is simply such that the first reactor bottom outlet, if connected to the feed, is connected to the feed of the second. The outlet of the second reactor is connected to the feed port of the top of the third, and the outlet of the third connected to the feed port of the fourth, forming the sequential series arrangement. The outlet of the fourth is then connected to the methanol bioreactor, where the particulates, which are bioorganics, are actually fermented into alcohol. The resulting gas stream effluent at the top of the cap is then used to produce the energy as the biogas biofuel that is expected, and the extracted solid particles handled as is appropriate. The conclusion that could be drawn here is that clearly, as of this point, the actions taken so far have enabled the farm to produce gas biofuel, which can be used in any design-specific combustion technology, coupled with an energy transducer to provide power, both mechanical and electrical, with the choice of final thrust left completely at the discretion of the farmer. The bioreactor system is indeed the better of the two options, as can be surmised from the features as delineated presently. First, it entails the use of smaller sized bioreactors and therefore more efficient use of available space. And second, the use of several bioreactors to capture the dynamics of a single batch reactor also inadvertently creates redundancies that allow for fail-safe exclusion of individual bioreactors, as when such units develop faults and require repairs. A single batch bioreactor developing any fault would result in the shutdown of the entire energy system pending the completion of repairs. Third, the continuous operating state of the bioreactor system ensures that the consequential energy production is also continuous and not intermittent, so then the farm will have power for operating at all times when need exists. Yet, the continuous system also requires more capital investment. So, the implementation of the bioreactor system requires some careful planning based on cost-benefit analysis. Spreading out the cost over time to match which performances offers capital investment management. In that regard, modular design implementation is cost-effective and offers the option of obtaining benefits and then plowing benefits back into the operation as reinvestment that empowers more growth and high productivity. So then the focus would be on a module to be replicated and concatenated, and the discussion of a module appropriately sets the foundation for the building of the bioreactor system. The design and fabrication of the various processes equipment adopted throughout the presentation are quite challenging, but can be realized even in rural communities with the skill set of a blacksmith working in consultation with an engineer or two. On the other hand, in fairly developed societies, the performing of the same task will be undertaken through a machine shop by a machinist also working in consultation with an engineer. Of course, the benefit outstanding is that the pumps of the water delivery and dispersing systems now also stand to be powered with the would-be derivative power, and remarkably without being obtained from use of fossil fuel resources, and indeed positioning the operation to transform subsistence farming into green subsistence farming. And it's a wrap. And on that note, I say to you, thank you so much for having come to listen to this observation about efforts aimed at alleviating world hunger through subsistence farming by both urban dweller farmers and emergent country small farms farmers. You are truly appreciated, and if you would like to get privileged viewer-reader information or access podcasts of specialized contents or access even vertically integrated concepts, then I implore you to join my supporter club and enjoy that privileged status. Moreover, while still here, do please take a moment and subscribe to the channel as to be informed of the publication of every new episode as soon as it is released. Thank you. Bye. Till next episode.